For those people who are watching on YouTube, if you want to join our webinars live, then you need to sign up for MESHWORK. MESHWORK is entirely free to join. It's a platform that was developed by Mesh Energy in order to help people who've got an interest in renewable and sustainable design to network freely and to discuss ideas and to share great content, case studies, etc. It's a really good platform, so please sign up. So what are we going to cover today? Well, after a short introduction to Mesh Energy, we're going to get into a little bit about spec and design. Sizing and heat demands. When would you use a bivalent parallel system? And we'll obviously define that. When would you use a bivalent alternative system? And we'll define that. And then we'll look at some of the effects on the ground loop sizing of bivalent systems, because a bivalent system will have some effect on how you size the heat pump, but also the ground loop that goes with that heat pump if it's a ground source heat pump. We'll look at a little bit about electrical supplies to heat pumps, and that might be one of the driving factors about why you might be looking at a bivalent system. And finally, we'll look at on the sort of technical side, we'll look at some of the controls. There'll be a very brief overview of controls because they do vary quite a bit from one manufacturer to the next. We'll then look at subsidies. At the moment, there's only really one government subsidy available in the UK, which is the Domestic Renewable Heat Incentive, or the DRHI. You'll hear me refer to RHI in general, probably, but now the non-domestic RHI has disappeared as of earlier this year. It's only the domestic RHI which is left. That is due for either phase out or replacement at the end of March 2022. As yet, no replacement has been announced, so we'd have to sort of think that the RHI will be going in March 2022. And finally, we'll go through some of the key points, just a few sort of key nuggets of information to maybe think about and take away from this presentation. A little bit about how you can work with Mesh, and then a little space for questions. So who are Mesh Energy? Well, if you're watching this live, then you probably already know this because you'll have engaged with us through MESHWORK. But for those of us, those that aren't so familiar, Mesh Energy is a renewable energy consultancy. We're based in Farnham in Surrey in the UK, and we're a small but growing consultancy. But we aim to provide impartial, holistic advice about low energy projects, and we do that through a number of means, starting all the way from feasibility, almost back of the fag packet sketches, all the way up through to full M&E design, and then even post-occupancy evaluation. The next thing I'm going to talk about is a little bit about the energy hierarchy. And again, we include this slide in almost every one of our presentations because it is absolutely central to the work that we do as Mesh, and also the way we feel that anybody tackling a green project should be working. And basically, starting from the left here, it's talking about all the passive things that you can do with a building to reduce the reliance on technology. So whilst this presentation talks about technology, really we should have been thinking about all these other things before we get to talking about technology, renewables, and all those kind of things. So that's right over here on the right hand side. So we've gone through all these things before we get to where we're talking about today. Now, clearly, in a retrofit situation, you maybe can't choose the orientation or the location of a building. You maybe can't choose the topology around it. you probably can't even choose much about, you know, the forms or the window sizes, or you might not even be able to control the insulation that well, because it might be that, you know, it's an existing listed building or something where you can't really affect a lot of those things. But you can affect the, you know, the bits you can affect, you should. But we'd always say, do all the fundamental building fabric and energy efficiency things you can first, and then start thinking about applying technology to the building. That said, let's talk a little bit about heat pumps, what they do and why we would use them, because they are the backbone of a bivalent system. So on the screen, you can see a simple refrigeration cycle. And in most cases, we would have we'd have something on the outside of the building on this side, and the building would be on this side of the refrigeration cycle. I hope you like my fantastic drawing. You can see why I'm not an artist for a living. So effectively what's happening is that heat is coming in to the refrigeration cycle here, and that can be from the air or it can be from the ground, and the heat is being amplified via the refrigeration cycle. So it's low grade heat here, and what's coming out on this side is high grade heat on this side, and that's the heat you're using to heat your building. An air conditioning system basically does exactly the opposite. So there it's harvesting the heat from the building, and then it's putting out heat into the environment. So most heat pumps are actually reversible, so you can use them for cooling as well. That's not what we're here to talk about today, but it is a nice little useful thing that you can use in some circumstances. So this slide really just goes through that, and it's really what I've just talked through. But it's all about heat transfer. Really, the electrical input is up at the compressor side, and the compressor is you know, that's probably taking around about a quarter of the energy of what's coming out at the far end. Obviously, you can't make or destroy energy, so 3/4 is coming in through the evaporator. You're adding a quarter at the compressor, and then the full amount is coming out into the building. And then there's a little bit of waste in the expansion valve. So most heat pump systems are what we call monovalent systems. And so I'm just going to describe what a monovalent system is to start with, and then we'll talk about bivalent systems. So a monovalent system uses a single source of heat generation. Now, for the systems we're talking about, that will probably mean a ground source or an air source heat pump, but equally a standalone boiler that most people in the UK have in their house is a monovalent system, but it's probably not what we're going to be talking about today. Ground source heat pumps are usually operated as part of a monovalent system, and we'll talk a little bit more about why that is further down the presentation. But just bear in mind that the majority of bivalent systems tend to be air source based rather than ground source based. As I say, air source heat pumps are frequently paired with a secondary heat source to create a bivalent system, and we'll give some examples of that further on as well. So what's a bivalent system then? Well, a bivalent system is quite simply a system that uses two sources of heat generation. And within that, that can be divided down into two primary categories. So the primary heat source, which is the heat pump, is then paired with that secondary heat source, which is often a boiler, but it can be operated either as what we call bivalent parallel or bivalent alternative. And what bivalent alternative is very simply where the heat pump works independently of the secondary heating system. So one or the other is running, but they never both run together. And there'll be typically this type of system is used in a retrofit situation where it might be too expensive to change the heat emitters. So the radiators, so you've got an existing house, it's got existing radiators, it was designed around a boiler. If you just bolt a heat pump onto the end of that, the flow temperature the heat pump will give and the COP the heat pump would give at those flow temperatures simply isn't enough to make the system worthwhile. So what you do is you have the heat pump operating when the ambient temperatures are warmer. You can then get away with the lower flow temperatures associated with the heat pump. And when the temperature goes up, then you start operating, it goes down, then you start operating the boiler. That allows you to get the higher flow temperatures that are required to meet the heating outputs required at low ambient temperatures. In a bivalent alternative system, the boiler has to be sized to cover the entire heat load of the property. So you can't add the output of the heat pump plus the output of the boiler together and say, well, yeah, together they match the heat load, because they'll never operate in tandem. They'll always operate separately. So the boiler must be sized to cover the entire heat load of the building. That does tend to add a little to the capital cost, but generally speaking, on a typical sized house, for example, a 15-20 kilowatt boiler is relatively cheap. It may well be that you're reusing the existing boiler that's already there. So the main reason for this is to give you higher flow temperatures. That's really the long and the short of it. That's why you'd use a bivalent alternative system. That's probably the biggest single reason for doing it. There's quite a nice case study that Graham Hendra sent me from Freedom Heat Pumps, which unfortunately I haven't been able to shoehorn into this presentation, but it actually shows how operating what they would call a hybrid system can give you lower running costs under certain conditions, especially in retrofit. So again, that's something that might be worth looking at in some retrofit situations. So Bivalent Parallel, I couldn't actually find a photo of a Bivalent Parallel system, so I've used two heat pumps in parallel as a sort of proxy. But in a bivalent parallel system, the heat pump and the backup boiler work together in tandem. So in that case, the output of the heat pump plus the output of the boiler need to equal the heat load of the building at design temperature. So these are typically used where the electricity supply limits the size of the heat pump that can be fitted. Now you might say, well, why not just put a three-phase power supply in, and then you're probably going to find you've got enough power then that you can operate a three-phase heat pump and everything's good. The reason for that is that sometimes the cost of upgrade to a three-phase power supply might be prohibitively expensive, and so you're limited effectively to a single-phase supply without spending huge amounts of money, and therefore it's more economically beneficial to have a bivalent parallel system. Smaller boiler is obviously required then for a bivalent alternative system, because the boiler on its own is never taking the full heat load of the building. The heat pump runs more hours during the year, and it tends to run at its maximum capacity for long periods of time. Now that can be good from an efficiency point of view, but it obviously just needs to be borne in mind, especially if there were, for example, limitations in the warranties on the heat pump for particular compressor run hours per year. So you just might need to just be a little bit careful about that when choosing the heat pump. Because the heat pump is providing a greater proportion of the heating in a bivalent parallel system, this can be good for domestic RHI payments. So that's a little positive just to bear in mind. Obviously, a monovalent system would give you potentially even better domestic RHI payments. And the main reason, again, as I said, the reason you probably do this would be for potentially lower capital cost. especially if you've got a limitation on power supply. Okay, so that's the kind of major reasons why we might look at a bivalent system in the first place. So let's delve a little bit more into the details and specification and design. So as with any spec and design for a heat pump, the first thing that you must do is work out how much heating you actually require for the property. So here we've got an IES model of a particularly lovely new build house that we did some designs for. So step one is to determine the design temperature based on the location of the building. So generally speaking, the further north in the UK you go, the lower the design temperature will be. So up in the north of Scotland, you might find that there's a design temperature of -5, -6, -7. And the other thing that happens is as you go up in elevation, then again, the design temperature will tend to drop. So if you're on the top of a mountain in Scotland, you are going to have a lower design temperature than if you're in the centre of London at pretty much sea level. The next thing to do is determine the peak space heating demand based on the standard room temperatures. So the peak space heating demand is basically how much heat is that room going to lose on the coldest day of the year. So you decided what the coldest day of the year is, which is the design temperature day, and you then work out how much heat is coming out of the room on that design temperature day, and that's based on standard room temperatures. So that's 21 for living rooms, dining rooms, 18 for kitchens, WCs, and bedrooms. Circulation areas tend to be 18, and then you might get odd rooms where you might want it cooler or hotter. So bathrooms, for example, are designed at 22 degrees, and then you might get odd rooms like swimming pool, changing rooms or something like that, which you might want even a little bit warmer still. You then specify the heating water flow temperature. Now that is probably going to be based on the heat emitters that you've got and how much heat you need to get out of them, and how much heat they can give out at different temperatures. As a rule of thumb, the higher the heating water flow temperature, the more heat you'll get out of a given emitter. So, you know, it stands to reason if you put hotter water into a radiator, it gives out more heat than if you put cooler water into it. You then need to add something onto the total heat load you've got to allow for the preparation of domestic hot water. And a rough rule of thumb is that about 200 watts per person is sufficient. That will vary slightly depending on the size of the cylinder you've got and how much consumption you expect each person to use. But the 200 watts per person is quite a good starting point. And then finally, you know what the total heat demand is on the system. You simply design, you simply choose a heat pump and a boiler that meet that heat design. So let's have a look at a bivalent parallel system. So this is so on this graph, you will see that there's 3 lines that are really important. So this blue line here is the output from the particular heat pump that we've chosen. So this is this red line that goes across here. So that's the output you'll get at different temperatures. Then you've got this black dotted line that runs down here. And that is the heat demand of the building. So you'll see this particular building, the design temperature is about -2 degrees, which would be typical for the sort of south of England. So the vertical line that runs down here, this starts from this point where the output of the heat pump and the heat demand of the building cross, and that point there is the bivalent point. So as we've talked about before, you can see at the top, the yellow shaded area is the amount of load that the boiler is picking up in this bivalent parallel system. So everything under the black line is the load, and then the yellow shaded area is what the boiler's picking up. And we'll see the contrast on how much the boiler picks up when we start looking at the when we look at the bivalent alternative system. So, as we said before, this would typically be used when the electricity supply can't support a monovalent system and cannot be upgraded, or when high domestic hot water temperatures are required. As you know, typically a heat pump will do about 50 degrees domestic hot water temperature, and then you use a thermal disinfection cycle once a week to get rid of Legionella. The third reason you might use a bivalent parallel system is if there's an existing combi boiler and there's not sufficient space for a domestic hot water cylinder. So then you could use, you could retain the combi boiler and use the combi boiler to prepare the hot water, but also as a backup for the space heating system. Or the last reason is if there's insufficient capital available to install a monovalent system, and there's an existing fossil fuel based system that can be easily adaptive. So that's sometimes the case that you know, because the cost of air source heat pumps and ground source heat pumps rises quite steeply with output, it might be that somebody says that I've only actually got enough money for an 8 kilowatt system, but I really need 12. You know, it might be that you could actually adapt the existing system around their budget by using a bivalent system. So that on this bivalent alternative system, you can see the same major features. So once again, we've got the building load coming down here on the black dotted line, the heat pump output in the blue solid line, the bivalent point where those two lines cross. But the big difference here is you'll see the boiler's picking up everything to the left-hand side of the line that's taken down from the bivalent point. So everything under the black dotted line to the right of that red line, so all the area in here, all this area in here is picked up by the heat pump. Everything in the yellow shaded area is picked up by the boiler. So the boiler's doing more work in the alternative system, and that's why it needs to be a little bit bigger. So this is typically used where an installation requires high flow temperatures. So you may well have picked that bivalent point because you know that from doing some work, that's the point at which the flow temperature from the heat pump will no longer give you enough heat to keep the building warm. So you can move that bivalent point up and down by selecting a different heat pump, because obviously each heat pump will have a different output curve. So you can see this particular heat pump's got a fairly flat output curve. A lot of them drop away quite significantly when you get down to minus 10, minus 15, but this one's relatively flat. So it's quite a good, well-designed heat pump. But you can see the output does drop as you get down to around sort of zero. Or just sort of 1 or 2 degrees. It's at its minimum, and then it starts going back up again a little bit. So you could, by selecting a different heat pump, you can move where that bivalent point is, and you can plot this out. So you plot what your you plot this point here first, which is the point where the where you've got your maximum demand. So in this case, it's 10 kilowatts at minus 2 degrees. You know that at 15 degrees, you're going to basically have no heat load from space heating, because buildings keep themselves warm just from solar gains, etc. At that kind of temperature. You can draw a straight line between those 2 points. That's pretty much it's pretty much linear. In reality, it won't quite be. You then have your heat pump output plotted on, and where those two lines cross, you've got your bivalent point. You may also use this where the electricity supply can't be sufficient to support a monovalent system. So again, the bigger the heat pump you put in, so you could move this line up by putting the blue line up by putting a bigger heat pump in, and you could get it so that it will do the 10 kilowatts at -2, but it will then use more electricity. It might be your electricity system can't support that, so you put a smaller heat pump in so that the electricity system will cope without upgrade. The third reason is about fuel costs. So it might be that, as it is in the UK at the moment, typically a gas boiler is going to cost you about 3 pence per kilowatt hour for fuel. A heat pump is going to cost you about 12 to 15 pence per kilowatt hour for fuel. So if your heat pump's giving you a COP of 4 at 0 degrees, but gives you a better but the COP will tend to rise with ambient temperature, what you might find is that when you work out the maths, it's actually cheaper to run a boiler below a certain ambient temperature. So you can then set your bivalent point based on where you want to switch over to the boiler, because it's going to be cheaper to run it that way. Bearing in mind also that what you can do with the heat pump is you can weather compensate it, so you can lower the flow temperatures as the ambient temperature starts rising. Again, we might use a bivalent alternative system when very high domestic hot water temperatures is required, or when there's an existing combi boiler. So all these situations can be beneficial for a bivalent alternative system. And finally, the additional capital requirement as well. So that's kind of gone through why you might use a bivalent system. It's gone through some of the advantages of bivalent systems. It's gone through a few of the complexities of bivalent systems, and especially around the maths of making the economics work or not work. So let's have a look at the ground source sizing. So bivalent systems derive most of their heat from the heat pump. So as you know, when you're sizing a ground source heat pump, most of the cost of installation on ground source actually goes into putting the pipes in the ground. It's one of the biggest single cost factors in the whole installation. So you think, well, okay, I'll put a bivalent system in. That means I'm going to have a smaller heat pump. It's not going to be taking as much energy from the ground, so I can then put a smaller collector in, which then means I'm going to get an economic benefit from not having to put in such a large collector array. Unfortunately, it doesn't quite work like that, and that's because your smaller heat pump is likely to be running for more hours in the year than the larger heat pump you would have put in for a monovalent system. So that means that the total amount of energy you're extracting from the ground, although it's smaller, it's not actually that much smaller. So you're still trying to take the same amount of energy from the ground, or approximately the same amount, so your ground loops don't get that much smaller. The other thing to remember is that, particularly if you're using a bivalent parallel system, the boiler is only topping up what the heat pump can't manage. So for most of the year, the heat pump's going to be running, or certainly for sort of 2/3 of the year in the UK, when we got the heating on, the heat pump will be running. So if you've got a bivalent alternative system, if you've got quite a high bivalent point, then it might reduce the sizing of the ground loops a little bit. But actually, even in February, the average temperature in the UK is still above 2-3 degrees. So if you've got your bivalent point set at 2 degrees, you're still going to be deriving, even in a bivalent alternative system, most of the heating is still going to be coming from the heat pump. So the sort of takeaway from this is the ground loop sizing is not going to vary by as much as you might think. That means the capital costs are not going to reduce by as much as you might think they will. Okay, so let's talk about heat emitters. This is something that is quite important, because this may well be the driving factor behind why you're choosing a bivalent system in the first place. So underfloor heating, well, the good news is that bivalent systems, monovalent systems, heat pump systems in general work brilliantly with underfloor heating systems. They are usually the most efficient option. The only caveat we need to think about with a bivalent system is potentially you're looking at higher flow temperatures in the heating system as a whole. That might be possible with a monovalent system, and therefore it is probable you're going to need to use mixed manifolds just to help protect the floor finishes. So when you get higher flow temperatures coming through the system, you don't end up damaging the floor from overheating the floor. Compatibility with radiators. Well, as we've already discussed, bivalent alternative systems are frequently used with retrofit installations where there's existing radiators. And those existing radiators are generally sized for boilers which have higher flow temperatures. And those higher flow temperatures, unless you can offset the requirement for those higher flow temperatures by improving the insulation of the building, those higher flow temperatures are still going to be needed to adequately heat the house or the building when you start getting into low ambient temperatures. So that's where they can come into their own. If you're building a brand new building, or you're replacing the heating system entirely, but you still want to go with radiators, the first thing I'd say is oversize the radiators, because that will reduce or eliminate the need for a bivalent system. And if you can eliminate the need for a bivalent system, a monovalent system is much simpler. It's probably going to be about the same cost to install, and it'll probably give you a better seasonal coefficient performance and lower running costs. If you've got existing systems, think about whether it's possible to just replace a few key radiators and still meet the heating demands of the room. Because it might well be that maybe the living room radiator is too small, and maybe one other radiator somewhere else in the house is too small, but actually all the other radiators will work, were sufficiently oversized at when the building was first built, that you could actually get away with the lower flow temperatures from a monovalent system. And again, you could potentially, just by changing a couple of radiators, avoid the need for a bivalent system entirely. So electrical supplies, I've talked about this a little bit already, but I just really wanted to sort of clarify where electrical supplies come into this. So most houses in the UK have an electrical supply from the distribution network operator, which could be rated up to 100 amps. Now, obviously, that 100 amps has to do everything from lighting, cooking in many instances, powering your TV and your computers and your mobile phone chargers and all the other things that you have electrically around the house, as well as running your heat pump and potentially an electric vehicle charger and those kind of things. So from a single phase supply, realistically, in most cases, the limit for output is going to be around about 15 kilowatts thermal for an air source heat pump, or maybe up to about 22 kilowatts thermal for a ground source heat pump. And that's simply a reflection of the fact that ground source heat pumps are a little bit more efficient. There's no need to upgrade the power in most cases. You may find some older properties only have a 60 amp supply, which in most cases the DNO will upgrade to 100 amps for free. So that there is a little bit of a caveat on that. It's worth, especially on houses which are over maybe about 200 square meters, or where there's lots of other electrical appliances, it might be worth doing a diversity analysis, which is basically an analysis where you look at everything that uses electricity in the house, works out when it is likely that those appliances are going to be used at the same time, and then comes up with a maximum demand figure for that property. You obviously want to make sure the maximum demand is less than the amount of power that's available to the house or the property. That way you don't end up blowing the main fuse or start melting things. Three-phase supplies. Well, if you've got an installation that's larger than the ones that I've listed above, or where there's lots of other electrical loads, so you've got a swimming pool, for example, as a good example, then it might be that a three-phase supply is the only way to go. The costs of upgrade to three-phase vary significantly from site to site. I've seen quotes as low as £1,000 and quotes as high as nearly £150,000. So that, you know, they vary by a huge amount. And obviously, if you're getting a very, very high cost of upgrade, then that's where a bivalent system may be a really good solution. Most domestic properties in the UK have a single phase supply when you first, a sort of standard. So if you do need to upgrade to three phase, then there will be a cost associated with that. So let's talk a little bit about system controls. So in most systems, you will get some sort of demand signal coming from the heating. But that goes back to the heat pump manager. So the heat pump manager acts as the master controller in the system. Now this whole section is quite generic because the way that different heat pump manufacturers and different heat pump controllers work does vary. But as a general rule of thumb, this is a pretty good place to start. So the heat pump manager acts as the master controller for the system. A demand signal is then given by some sort of thermostat, and that could be an underfloor heating manifold controller. It could be a master thermostat in a common area on a radiator system. It could be individual electronic thermostatic valves on radiators in some newer systems through a Nest system or something like that. But you'll get some sort of demand signal coming back from the heating system saying there is a demand for heat, and that goes to the heat pump manager. The heat pump manager then decides whether it is going to use the heat pump to satisfy that heating demand, whether it's going to use the boiler to satisfy that heating demand, or whether it's going to use, in the case of a bivalent parallel system, a mixture of the boiler plus the heat pump. So in the screen on the right hand side, so this is a screenshot taken from an EcoForest heat pump. You can see here that it allows bivalent parallel operation when the ambient temperature outside is below 8 degrees. It will allow the boiler to start when there has been a continuous demand for heating for at least 30 minutes. So you've got sort of two if functions here. So if the external temperature is below 8 degrees, then you allow the heat pump to start. If there's been continuous demand for more than 30, and there's been continuous demand for 30 minutes, then you can allow the boiler to start. And the final thing is that it's saying if the required flow temperature is more than 5 degrees away from what the target flow temperature is, then it allows the system to start, the boiler to start. So say your target flow temperature was 50 degrees, it would need to be at 45 degrees or below for 30 minutes, and the ambient temperature outside would need to be below 8 degrees. And then if all those conditions were satisfied, it would allow the boiler to start. You'll see here it also allows for a bivalent parallel, a bivalent alternative system. So what they call a replacement system. So the boiler replaces the heat pump. But you see in this case, effectively, it's been it's been told that it will never get to that situation because it's been set to -99. So it will never replace the heat pump with the boiler. But if it was an air source heat pump, then maybe the most economic way of running it would be to increase that replacement temperature up to somewhere around -2 or something, and you'd have to do the sums for your particular boiler, your particular heat pump, your particular heating system. As I say, these exact connections, the exact control strategies, and even the exact hydraulic systems vary from heat pump to heat pump and from installation to installation. And they will also vary depending on whether you want the boiler to continue to do the hot water all the time, or whether you want it to do the hot water, just in certain situations. Okay, so that's the technical bit done. You'll be pleased to hear. So let's talk a little bit about what the government will pay us for installing some of these systems. And at the moment, there's only one way of doing this, and that's through the Domestic Renewable Heat Incentive, the DRHI. So the Domestic Renewable Heat Incentive is paid over 7 years. Its payments are designed to reflect the increased cost of installation of a renewable heating system versus a conventional fossil fuel-based system. The payments are tax-free, so you don't have to declare them on your income. And this is how it works. So for each technology, there is a maximum amount that can be paid. So for an air source heat pump, for example, it's £10,100 at the moment. For a ground source heat pump, it's £32,000. That reflects the fact that ground source heat pumps are more expensive to install than an air source heat pump. Biomass is 11,450. But you'll see the amount you get per kilowatt hour for biomass is pretty low, and solar thermal is only £2,100, but you do get an awful lot per kilowatt hour for solar thermal. So you then have to look at how much energy you're actually producing from your heat pump, and that is just done on a per kilowatt hour basis. So for an air source heat pump, you get paid 10.71 pence per kilowatt hour, up to the maximum of £10,100 over the 7 years. For a ground source heat pump, you get up to 20.89 pence per kilowatt hour, up to your maximum of 32,000, etc. But obviously, when there's a hybrid system or a bivalent system, you also need to know not just how much heat is going into the system in total, but actually how much that is coming from the renewable source, i.e. the heat pump. So you will need to install some heat meters. So this little box here on the right hand side is a heat meter, and they are eligible for domestic RHI payments. So you have to install the heat meters on the system to measure the renewable element of your installation. You also have to install electricity meters, so you know how much electricity your heat pump's using, and effectively the amount of heat you get out of the heat pump less the electricity going in is what you're getting from the renewable sector, and then you times that by the pence per kilowatt hour. Okay. Well, that pretty much covers everything we're going to talk about today. So I'm just going to run through the 6 or 7 sort of key considerations, the key things I'd like you to try and remember after this CPD. First one, it's always the first one on the list: improve the building fabric before designing the heating system. There's no point in trying to heat a leaky building. Number 2, if retrofitting, consider the existing heating system. Are the heat emitters big enough already to allow for a monovalent system, or could you just change just a few key heat emitters to allow a monovalent system to be used? Cut down on complexity, potentially cut down on installation cost. Keep things simple if you can. Thirdly, check the electrical supply. Is an upgrade going to be needed to allow a monovalent system? If it is it more economic to pay for that upgrade, or would a bivalent system be a better alternative? Fourthly, analyze whether a bivalent system is the most efficient solution. Now, quite how you define efficiency in there might depend upon you or your client's ambitions for the project. If you want the most CO2 efficient installation, then it may well be that a monovalent system is always the most efficient from a CO2 point of view, especially if you're deriving a lot of your electricity from renewable sources, because CO2 efficiency obviously depends on where you're getting that fuel from. But if you're talking about simple economics, it may be that in some cases a bivalent system can be more economically efficient to run than a monovalent system, especially on a system on an existing retrofit type situation where you've got radiators that require quite high flow temperatures. Remember to use domestic RHI to help with financing. Now, obviously, that also feeds into the most efficient solution, because if you're taking into account domestic RHI, then that will probably skew what's the most efficient solution from a financial point of view. And finally, if you are using domestic RHI, just remember that you will need to have the appropriate heat meters fitted so that you can give the required information to the domestic RHI assessors, and you obviously won't get access to that RHI funding if you haven't got the heat meters in place. So before we talk about questions, obviously you've all seen this slide before. These are the services that Mesh offer. So where we've really been talking about today is really in this sort of stage 4, this M&E package kind of area here, around design specification of the heating system. But equally, Richard, Jen, and Ileana would be looking at what's the best solution at feasibility stage, and what was going to fit from a physical space point of view. So that's their sort of stage 1, 2, and 3, where you're kind of probably making the strategy call. Then stage 4, where you're actually going to be designing the system, and then finally at stage 7, where we're doing the energy monitoring. That would be all these sort of systems. It's a good idea to energy monitor them. It might be that you could just slightly tweak the bivalent points, give a better efficiency. Because what's installed and what's designed may differ slightly. Internal gains might be different, for example, from what you thought. We've got 3 very interesting upcoming webinars. So next week is how to deliver REBA 2030 on commercial projects. Then there's a repeat of the biggest eco project pitfalls, which Doug's presenting. And then we got an introduction to the latest version of the embodied carbon calculator for early stage design. I can see a number of people are already signed up to those. So without further ado, I will open the floor to questions. I see there was a question about CO2. And it looks like Richard's already jumped on answering that from his experience. So, so I won't go into that in too much detail. But obviously, there is a CO2 implication if you're installing a fossil fueled device against a heat pump. But as I say, it all depends on the fuel factors. If you'd asked me this 10 years ago, the answer would have been very different from what it is now. Clearly, gas boilers haven't changed a massive amount in the last 10 years in terms of efficiency, nor have heat pumps, but the fuel factors associated with electricity have changed significantly as the UK has greened up its electricity generation. So question about, would a bivalent parallel system be the best solution for a retrofit where there is no room for a hot water tank? So if you haven't got room for a hot water tank, then yeah, that's a bivalent parallel system might work very well, because you can then use a combi boiler to provide the hot water, and it could also provide backup to the heat pump in times of extreme weather, to give you a little bit of extra heating, which means you could then reduce the size of the heat pump, potentially saving some capital cost as well. So it'd be a very good option for that. Thank you for taking your time to listen to our presentation, and I look forward to seeing you at a future presentation with Mesh Energy.